I'm Antonio Sala, and in this video we are going to obtain the time response of an electrical circuit when subject to a train of sinusoidal pulses, like the one we are seeing here. In previous companion videos, we modeled the circuit and we obtained the time response to a single pulse, so you are advised to watch them previously in order to better understand this one. If we recall the modeling phase, this was the circuit to be modeled, these were the first principal equations, and this was the normalized first-order state space representation. If we give some numerical values and carry out Laplace transform of the normalized state space representation, or just of the equations and then solving for whatever we wish, we end up getting a model in the Laplace domain so that the output is a transfer function times the input Laplace transform plus some initial condition term like this one. A single sine pulse has this time expression. Here we have the single sinusoidal pulse, and MATLAB knows how to compute its Laplace transform. It's somehow similar to the Laplace transform of the whole sinusoidal starting at t equals 0 and lasting forever. It has some delay-related terms in the numerator. Let us first consider how to compute the Laplace transform of the pulse train we are watching now. In order to compute such Laplace transform, we need to realize that the pulse train is the sum of the pulse plus the same pulse delayed 10 milliseconds plus the same pulse delayed 20 milliseconds, so capital T. In here it's 0.01 seconds, and then this infinite sum is the time domain expression of our pulse train. The good thing is that in Laplace transform, delaying means multiplying by this exponential of s. So if pulse of s is this Laplace transform, then the first pulse is pulse of s times 1, the second pulse is the same delayed one period, delayed another period, and so on. So we have an infinite sum, but if we recall, the sum of a geometric progression has this expression, and in this case, this thing is 1 plus this exponential squared, plus, etc. So applying this formula, we get this thing. Then we have the Laplace transform of the sinusoidal pulse train, just multiplying this thing times this 1 over 1 minus the exponential of minus ts. If we check it, this is what we just said, so this is the Laplace transform of the sinusoidal pulse train, and if I plot its inverse Laplace transform from the symbolic toolbox, then MATLAB is happy to present us this figure confirming that we did it correctly. So we have the Laplace transform. However, we are not going to use the Laplace transform because, at least in a first code draft, the output in the Laplace domain will be transfer function times the input Laplace transform, and its inverse Laplace transform is kind of a horrible monster with some strange symbols, and the thing is that if I tell MATLAB to plot it, it just gets crazy, says some error. I mean, symbolic toolbox seems not to be able to handle this, and even if we might be tempted to look further in the theory to see how to compute the inverse Laplace transform of this stuff, the thing is that we are going to dismiss altogether this train of S and compute the Laplace transform via causality and state concepts, in the sense that, well, this first pulse is identical to a sinusoidal wave, so the first 10 milliseconds will be identical to the time response when the input is a sine wave, and then I will compute the state of the system after 10 milliseconds and repeat the computations with that new initial condition being the final state of the previous period. We did it in a previous video, computing the time response of this transfer function to a sinusoidal, which has this Laplace transform. So this is the time response to a sinusoidal with 0 initial conditions. And if we add the initial condition terms in here, we get the output to a sinusoidal, but from this point onwards, the red plot is meaningless because my actual input changed formula. It's the second pulse. So I will use this as an initial condition. So for the second pulse, the computations will be identical, but I need to put a different initial condition that I would call, instead of V0, V1. Let's do it. My fragment 1 will be the first 10 milliseconds of the time response to a sinusoidal. I already highlighted that above. I will solve the problem with 0 initial conditions, so I will not add any initial condition term, and after 0.01 seconds, the capacitor voltage will be 0.391 volts, so that will be the initial condition for the second fragment. Then this will be the time response of the second fragment. New initial conditions, but a fourth term responds to a sinusoidal identical to the previous one. So if I start with this capacitor voltage and I get a sine pulse, then the past is irrelevant. Everything is summarized in this initial condition. The future only depends on this initial charge of the capacitor and the future input, which is a pulse. Okay, so this will be the time response of the second fragment, which will be invalid after 0.01 seconds. And in that case, the capacitor will attain 0.53 volts, and we can repeat that forever. If I plug in this final condition after 2 sinusoidal pulses to the initial condition term, and I add the 0 initial condition to a sinusoid, then I get the next 10 milliseconds of response, which will be the fragment 3. The capacitor will end up 0.58 volts, and so on. We can copy paste another fragment 4, 5, 6, 7, 8, and get the final capacitor voltage at each fragment, which will be the initial condition of the next fragment. This seems to converge. We'll study steady state later on, but if I plot what I computed, first fragment, second fragment, of course, delayed 0.01 seconds because those initial conditions, the clock of the Laplace transform in MATLAB starts at 0, but the real clock started at 0.01, and in the same way each fragment has a different actual starting clock in my simulation, even if I compute some initial condition stuff, and MATLAB assumes that my clock starts at 0, so I need to do these code modifications, this delayed, in order to stitch the fragments of the time response. So here we have them. We have the first fragment, in which the first pulse, sinusoidal stuff over there, up to 1 volt, not to scale, will charge the capacitor up to this. Then the second pulse will have a fourth term, which is identical to the first one, but a different initial condition. Then the new charge of the capacitor is distinct. Third fragment, same fourth term, but different initial conditions, and so on, so on, so on. We can draw this line in which the green dots are the stitching point, in which the initial state of one fragment is forced to be equal to the final state of the previous one. As we can see, we reach sort of steady state where the green dots always have the same level, and that would be the non-sinusoidal steady state. It is non-sinusoidal because the input is a periodic signal, but not a sinusoidal one, so the response will have harmonics. And we will next compute the formula of that steady state. But let us first recap how we computed this. This thing is the time response to a sinusoid starting at 0, lasting forever. But then there is fragment 1 will be valid for just one period, so when it ends, we get this capacitor voltage and we stop using that fragment 1, and then fragment 2 will have the final condition of the previous fragment as the initial condition of the next one. And of course, as the input has the same formula, fragment of a sinusoid, then the force term will be the same. So we can go on computing fragment 2, 3, 4, or 1000, one after another, sequentially. The thing is that this Laplace transform stuff assumes that these initial conditions and this input started at time equals 0. So in order to correctly stitch the fragments, we need to carry out this delay to place the fragment at the correct location in the horizontal axis, and we get this plot. So let us now compute the steady state regime by solving an equation, in the sense that, okay, we see that each final state, 0.6, 606, 608, 609, 6095, it seems that if we compute a couple more fragments, we will get final state which is coincident to the previous one, so we will have reached steady state, at least up to 4 significant digits. But we can compute in one shot that steady state initial and final conditions as follows. If I introduce a symbolic variable v state, then if I knew that steady state capacitor voltage, something close to this thing, we are almost there, if I knew that, this would be y permanent, let's say, of t. This would be the fragment fourth term with the sinusoid plus the initial condition term, and what we need to hold so that we are indeed in steady state is that after 0.01 seconds, this steady state output coincides with the output at the start of the period. Of course, if this were second order, we would need coincidence not only on the output, but the output and its derivatives. But okay, just solving these equations, this VSS is a symbolic variable. Here we have it. And if we find the value of VSS so that when I replace time by 0.01, the result of evaluating this expression coincides with VSS, which is the initial condition, VSS, then we will get the steady state, and then, well, if I replace time by 0.01, all of this evaluates to a number, in particular this one, of course, because it's the fourth term after 0.01 seconds, and then this thing evaluates to 0.36 times VSS. So the only thing we need to do is equating this initial condition to this final condition. It's easy to solve. It's 0.6096. So we were almost there in our previous fragments. Then replacing this capacitor voltage in the initial condition term, we do it in this line, and we get this expression for the steady state, non-sinusoidal because of this exponential term, regime. And of course, all fragments of the response have the same formula except for this initial condition term of times exponential that, okay, change in each fragment. And this one is the one that would repeat forever. If we plot it just for 10 milliseconds, we have the input, the sinusoidal pulse, and something that starts in VSS and also ends in VSS. So when subject to repeated input pulses, the output would be a repetition of the red line, as we have that exponential term. This is a non-sinusoidal steady-state regime. And of course, if we stitch several fragments of it with suitable delay, we can plot this input pulse train and this steady-state solution that would last forever. And it will be the limit to this first solution, and okay, we are almost there. I mean, a couple more fragments and we would have reached steady state. So this is it. In this video, we computed the output to 0 initial conditions and this sinusoidal pulse train. We did it by stitching fragments of the response to a whole sinusoid, but changing the initial condition. So finally we obtain this time response, in which all fragments have an identical force term plus a changing exponential term due to the change in the initial condition. And if we solve the equation so that this initial state is equal to this final state, then we get a periodic but non-sinusoidal steady-state behavior of this circuit. So this is it. We end the video here. Thanks for watching.